Hello and welcome to this new channel called OS from Scratch. In this channel I'm going to take you through all the stages that go into creating an operating system. We'll start with the bare metal and work our way all the way up to running user applications. But first, let's have a look at the core around which this whole project revolves. The computer which we shall be writing the OS for, the OrangePi Zero 2 from Shenzhen Shulong Software Co. Limited. Like most low-cost computers, this one too is based around a SoC, or system on a chip. This means that this chip here is essentially the entire computer. Almost everything the board can do is implemented inside this one chip, in our case, the all-winner 8616. Going over the board's layout with a bit of a practiced eye reveals this as, aside from this one chip, there are very few other chips on the board, all having very narrow functionality. Going over them, we have two chips providing half a gigabyte of RAM each, the power management unit. These two are labeled Ethernet and Wi-Fi on the product's website, but as we'll see further on in the series, their function is technical rather than substantial. The actual networking is done by the controller that resides inside the H616. On the back of the board, we have this chip, which provides 2 megabytes of flash storage. Aside from the chips on the board, we also have a few interfaces. With the exception of the wired and wireless Ethernet ports, all those interfaces are directly controlled by our one single chip to rule them all. With that said, let's go over these interfaces. Here we have one USB port, the wired Ethernet port, and the antenna for wireless Ethernet and Bluetooth, a micro HDMI port. On the back we have an SD card port, and we have two headers for connecting various devices. The 26-pin header here mostly exports generic in-out pins, while most of the 13 pins in the header here have a more concrete predefined purpose. Last, and by no means least, these three pins are labeled Debug TTL UART. They provide the serial port for debugging the operating system. It may not surprise you to know that the OrangePi already has a few operating systems ported to it. As you can see, the board already has two Linux variants and an Android port. Since we're mostly using the standard OSes for reference, it doesn't really matter which one we pick. Whenever I'll be working with Linux on the board, I'll be working with the Ubuntu image downloaded from here. It is also worth noting that the computer I'll be working from is running Ubuntu Linux, and I'm using KDE. Most of what I'm doing here can be adapted with varying degrees of effort to any other modern operating system. One more download available here is the board's user manual. All in all, this document is not as useful as its name might suggest, but if you're having trouble following along with getting Linux running on the Pi, this manual does contain a few useful tips. It does, however, contain this useful map of the pins of the 26 and 13 pin headers. As we write our OS, we will be focusing more and more on core functionality of the board. The first purely technical document we're going to need for that purpose is the board schematics. Don't be afraid if this document seems completely unreadable to you. Learning how to navigate these documents is, after all, one of the goals of these series. For now, all you have to know about this thing is that it shows us which pin of which component is connected to which other pin. We'll pick out the details as we need them. As I said before, the heart of the OrangePi Zero 2 is the all-winner H616 chip. To understand it, we will need the documentation of how to work its various functions. There are two relevant documents. The first one is the chip's datasheet. At 67 pages, it may seem a little intimidating. I have two pieces of good news, however. A, we don't really need it. This document mostly talks about electrical, mechanical, and temperature tolerances. These are things that are of interest if you're designing a board using the H616, but not so much if you're trying to program an already built board. And B, if you think 67 pages are a lot, just wait till you see the H616 user manual. At 831 pages, this document sure is intimidating. Again, don't worry. Teaching you how to navigate such huge documents without reading them cover to cover is precisely why I'm here for. The H616 is built around a 4-core ARM CPU based around the Cortex-A53 architecture. There are two more documents you would be served to download, even though we won't be relying on them too heavily, at least not at first. The first is the ARM Cortex-A53 Technical Reference Manual, just 623 pages. Since the Cortex-A53 is implementing the ARM v8 level machine language, another document that would be handy to keep around is the ARM A64 Instruction Set Architecture. At almost 3,000 pages, it is our thickest document yet. It may surprise you then to learn it is probably our least useful document of the bunch. We will be writing very little assembly and reading only slightly more. General familiarity with the architecture you're working with is never a bad thing, but of all the documents we've seen so far, this one is really here only for reference, and only occasionally. I've placed links to all these documents in the description below the video. So, with that out of the way, let's run the board through its paces. The rationale for doing so is simple. We're about to try and operate the board and its interfaces from our own OS. Before we try and do so, we'd best make sure we can properly manipulate the hardware for an OS that is known to work. The first thing to do is to install Linux on the Pi. I'll be using a slightly different procedure than the one given in the board's user manual. First, I'll insert the SD card to my computer. I've already downloaded the Linux installation image, and I'll just extract it to a temporary directory. At this point, I need to write the image to the SD card. The SD card driver is called MMC in Linux, so the card appears as dev MMC block 0. I don't have any other MMC devices on the system, so assuming this is my SD card is fairly safe. Another better way is to make sure that the device only appears when I insert the SD card. As you can see, when I take it out, dev MMC block 0 disappears. When I put it back in, it reappears. Having verified that I'm not deleting my entire disk, I can write the Linux image to the SD card. I'm using the dd commands as that's what it does best, and it's the best at doing that. Does that make sense? This is the command to copy the image to the SD card. IF means in file, OF means out file. I'm also setting it to show the status of the copy as it's happening. This is a fairly quick SD card, and yet the speed we're getting is a little underwhelming. Regardless of whether that's justified or not, there's a way to make it quicker. Before writing the image, let's erase the SD card. The precise reason for doing so is a little complicated, but the bottom line is that writing to an empty card is faster than writing to a card that already contains data. Since I don't need anything currently on the card, it makes sense to start by completely erasing it. The command to completely erase pretty much any flash storage device is called block discard. I'm going to give it the -v option so it is a little more verbose. Next, I need to give it the block device to erase. This is where the extreme caution part comes in. Typing in the wrong name here can easily erase your entire hard disk. As you can see, this is a fairly quick operation. Next, let's write the image again. As you can see, we're getting considerably faster write speeds this time around. And I'm going to speed this up. No sense in you wasting so much time. With the copy done, I can just insert the SD card into the Pi and connect the power. Before I do, however, I'd like to have a way of tracking the boot process. One way is to connect it to a monitor. That's not, however, the path I want to go. Instead, I want to use the serial console. That requires some explanation. Serial is a collective name to protocols that pass the bits one after the other. In this particular case, we are using a variant of the RS232 protocol. There is also a protocol called UART. For our current discussion, the differences between those protocols are not important. Once upon the 19s, computers all came with a serial port. Sure enough, here is a computer, and while it's not strictly speaking from the 90s, it is close enough. As you can see, this computer is very usefully holding up a monitor and not much else. The serial port is the 9-pin D-type male connector here. This is not to be confused with the same size female 15-pin connector used for VGA. There is also a 25-pin female connector for a parallel port, which was mostly used for printers of the era before USB killed them all. It is vitally important to know just how unimportant it is that the RS232 originally came as a 25-pin D-type connector. There was no chance of confusing with the parallel port, however, as the 25-pin serial port was a male, like the 9-pin one. Modern computers, of course, do not subscribe to such foolery. Instead, what we have today are adapters from RS232 on one end to USB. These allow us modern people to hook up to UARTs of yore. Of course, our Pi doesn't have a D-type connector of any number of pins. In fact, all it actually has are pins. What we need to do then is figure out which pin in the D-type connector carry which signal and connect them to the 3 pins we have on the Pi board. Before we do, however, there is a problem. Remember I said the differences between the RS232 and UART were not important? Those differences have to do with the voltages used during transmissions. The OrangePi, however, uses voltages that fit neither standards. Without a voltage adapter of some kind, which in electronics is called a driver, things might simply not work. The OrangePi user manual recommends the use of a small adapter that contains both the voltage driver for the serial and the USB to serial adapter. You just plug it into your USB port on one end and to the TXD, which is transmit, RXD, receive, and G&D, ground pins, on the Pi, and you're ready to go. This device is based on the CP2102 chip. I've found it for around $5 each on Amazon, or 3 variants of the same chip for less than $3 total on AliExpress. So they are by no means expensive. With that said, I'm going to go a slightly different route. Due to a project I was involved in many years ago, I still have just a driver lying around, and that's what I'm going to be using here. The debug UART pins are documented on the board itself, here. So we hook up the TX, RX, and ground like so. There is one snag, however, to using the driver. I also need to supply it with 5 volts. The UART port does not have such a pin. The 26-pin header, however, does. If we go back to the user manual, we see it is documenting pins 2 and 4 as 5 volts in-out. In this case, we definitely want it to be out, as we want the voltage the board is already receiving. We now hook up the driver to the USB serial adapter, and we're ready to go. Almost. We need a way to display the data from the serial. Once upon a time, that was done using terminals. These were dedicated screens with a keyboard and a serial port, and later an Ethernet port on the back. They used a specific protocol to convert the raw data into terminal commands, such as display characters, change color, move the cursor, and so on. These days, everyone has a computer that already has a monitor and a keyboard. Having the dedicated terminal makes no sense. Instead, we run programs that behave like a VT100 type terminal would. These are called terminal emulators. The Pi user manual recommends we use PuTTY. It is indeed the go-to program for serial as well as SSH communication, and for good reasons. It is open source, it has excellent terminal emulation, so the text doesn't get garbled, and it's available for Windows, Linux, and Mac. Obviously, a sound, safe choice. Except I don't need PuTTY. I'm already working with a terminal emulator on a daily basis. It's how I've been communicating with the Linux shell since time immemorial, or at the very least, the beginning of this video. It is an excellent terminal emulator, and it makes no sense for me to switch merely because my data is now arriving over a serial port. Instead, what I need is a program that will connect to the serial port and just dump, unthinking and unfiltered, what it gets from the port to the terminal. My usual terminal emulator will know what to do with it. Luckily, such a program exists. It's called Microcom. To run it, I just give it the name of the serial device to use. In my case, dev TTY USB 0. It even defaults to the same bitrate, or baud, that everyone seems to default to, which is 115,200. One last note before we begin. If you intend to use the serial on Linux, you would need to be in the dial-out group, or you would get permission denied opening the serial port. With that out of the way, we're ready to hook the power up. Almost as soon as we hook up the power, the red light comes on, and we start seeing text scrolling on the serial console. The boot process has several distinct stages. We won't go into all of them now, but just you wait. We can see that the LED now switches to green at about the time the Linux kernel starts loading. First boot after flash takes a little longer, and the kernel is configured to issue the boot message to an HDMI monitor, which we did not connect. So we are left staring at nothing for a few seconds until we get a prompt. Username root, password OrangePi, and we're in. The first thing we want to do is configure the Wi-Fi. It is managed using a service called Network Manager. To configure it, we'll be following the manual recommendation and use a command line tool called nmtui. With the network connected, we want to switch our shell into the Pi to an SSH-based one. The Pi is a little awkwardly named OrangePi Zero 2. Since typing this is already a handful, we're going to ask SSH to skip asking for the username each time. We can also use public key authentication to save us on typing the password each time. One last thing, it seems that Linux on the Pi is not very quick to save the data to disk. I've had cases in the past where I had to repeat those stages because the SD card did not update. The sync command should make sure that the SD card is up to date. We'll also make sure to properly shut down when we're done. With the preliminaries out of the way, it's time to start checking the peripherals. The first thing we want to check is that we can control the onboard LEDs. Controlling LEDs in Linux is done via the sysfs sudo file system. This appears to be directories and files, but are actually handled by the kernel drivers that control the hardware. Going to sys class LEDs, we see two directories, representing the red and green LEDs. Looking inside these directories, we see a file called brightness. Some LEDs can produce different brightness levels. Our LEDs, however, cannot. Writing 0 to the file turns the LEDs off, and writing anything which isn't 0 turns it on. These two are enough for us to get visual feedback from code, which is all we're really after at this point. With that, we can theoretically conclude this introduction video. Before we conclude, there is one more thing I want to do. The OrangePi Zero 2 has no hardware reset button, so the only way to cause it to reboot is to remove and reinsert the power. This is, to put it mildly, inconvenient. I have a BreadBoard starter kit that arrived with this handy 3.3 and 5 volt power supply, fed from a USB cable. Looking at the pin chart of the board's user manual again, we see that pins 2 and 4 are marked as 5 volts in-out. So far we've used them as an out pin, feeding voltage to my serial driver. We can, however, also use them as in pins. Pin 6 is a ground pin, so if we connect our breadboard's 5 volt and ground to pins 4 and 6 respectively, we should be able to control turning the Pi on and off using this switch. With the board running Linux, allowing us to easily turn it on and off, connect to it and control the LEDs, we can finally conclude this first video in the series. In our next video, we'll try to replicate turning the LEDs on and off without going through either U-boot or Linux. I'm supposed to say something about liking, subscribing or something. I can't figure out what it was supposed to be. Oh well, couldn't have been particularly important. Thank you for watching, and we'll see you in the next video.